This lesson is on solving for the pH of an acid-base titration involving a weak acid, C6H5COH, or benzoic acid. Benzoic acid, C6H5COH, is a weak acid with K equaling 6.3 times 10 to the minus 5. Consider a titration of 25 ml of 0.10 m C6H5COH by 0.10 m NaOH. Answer the following questions. A. Write out the reaction associated with Ka. B. Calculate the pH after the following total volumes of NaOH have been added. 1. 0 ml. 2. 12.5 ml. 3. 25 ml. And 4. 35 ml. The NaOH equation with respect to K is C6H5COH, AQ, plus H12L at equilibrium forms C6H5COO minus AQ plus H2O plus AQ. The first problem is to calculate pH after 0 ml of 0.10 m NaOH has been added. To solve this problem, one needs to construct a Rice table. The initial concentration of C6H5COH is 0.10 molar, and for C6H5CO minus and H2O plus are both 0. The change is minus X for C6H5COH, and for both C6H5CO minus and H2O plus, it is plus X. The equilibrium concentrations are 0.10 minus X for C6H5COH and X for both C6H5CO minus and H2O plus. The equilibrium expression is the concentrations of C6H5CO minus times H2O plus over the concentration of C6H5COOH equals X squared divided by 0.10 minus X equals 6.3 times 10 minus 5. To determine if X is small, we need to take the ratio between benzoic acid's initial concentration and Ka to determine if it is greater than or equal to 400. It turns out that after doing this, the ratio equals 1587, which is greater than 400. So the assumption X is small is confirmed. The revised equation is X squared divided by 0.10 equals 6.3 times 10 minus 5. In solving for X, take the square root of the product of 0.10 times 6.3 times 10 minus 5 equals plus or minus 2.5 times 10 to the minus 3 molar. Using only the positive root, X equals 2.5 times 10 minus 3. The pH of this solution is by taking the negative log of H3O plus or the negative log of 2.5 times 10 to the minus 3 equals 2.60. The second problem is to calculate pH after 12.5 ml of 0.10 m NaOH has been added. Note, mmol equals volume in milliliter times molarity in units of moles per liter. The construction of an mmol stoichiometric table is performed. The mmol of C6H5COH is by taking 0.10 molar times 25 ml equals 2.5 millimoles. The mmol of OH minus is by taking 0.10 molar times 12.5 ml equals 1.25 millimoles. The amount of OH minus is the limiting reagent, so after subtracting both substances by 1 0.25 millimoles and adding 1.25 millimoles to C6H5CO minus results in a final amount of 1.25 millimoles for C6H5COH and C6H5COO minus. The molarities of both C6H5COH and C6H5COO minus are 0.033 molar each. Since the molarities of C6H5COOH and C6H5COO minus are both equal, under the Henderson-Hasselbalch equation, the log of the ratio between the concentration of C6H5CO minus and C6H5COOH equals log of 1 or 0. Therefore, pH equals pK, or the negative log of 6.3 times 10 to the minus 5 equals 4.20. The third problem is to calculate pH after 25 ml of 0.10 m NaOH has been added. The construction of an mmol stoichiometric table is performed. The mmol of C6H5COH and OH minus are by taking 0.10 m times 25 ml equals 2.5 millimoles each. The amount of C6H5COH and OH minus are both the limiting reagents, so after subtracting both substances by 2.5 millimoles and adding 2.5 millimoles to C6H5CO minus results in a final amount of 2.5 millimoles for C6H5CO minus. The molarity of C6H5CO minus is 0.050 molar. At equivalence point, one needs the Kb of C6H5CO minus. The Kb of C6H5CO minus is Kw over Ka, or by taking 1.0 times 10 to the minus 14 and divide by 6.3 times 10 to the minus 5 is 1.6 times 10 to the minus 10. To determine if x is small enough to ignore, one takes C6H5CO minus initial concentration and divide by Kb, or 0.050 divided by 1.6 times 10 to the minus 10 is 3.1 times 10 to the plus 8, which is greater than or equal to 400. Thus, the assumption that x is small to ignore is validated. The equilibrium expression revised is Kb equals the concentrations of C6H5COH times OH minus divided by C6H5CO minus equals x squared divided by 0.050 equals 1.6 times 10 to the minus 10. The final value of x is plus or minus 2.8 times 10 to the minus 6 molar. Using only the positive root, x equals 2.8 times 10 to the minus 6 molar. The pOH of this solution is equal to the negative log of OH minus or negative log of 2.8 times 10 to the minus 6 is 5.55. The pOH of this solution equals 14 minus pOH, or 14 minus 5.55 equals 8.45. The fourth problem is to calculate the pH after 35 ml of 0.10 m NaOH has been added. The construction of an mmol stoichiometric table is performed. The mmol of C6H5COOH is by taking 0.10 molar times 25 ml equals 2.5 millimoles. The mmol of OH minus is by taking 0.10 molar times 35 ml equals 3.5 millimoles. The amount of C6H5COH is the linear agent, so after subtracting both substances by 2.5 millimoles and adding 2.5 millimoles to C6H5CO minus results in a final amount of 1.0 millimoles for OH minus and 2.5 millimoles for C6H5CO minus. The molarity of OH minus is 0.017 molar, and for C6H5CO minus is 0.042 molar. Since hydroxide ion is in excess, one can determine the pH of this solution. The pOH of this solution is by taking the negative log of OH minus or negative log of 0.017 molar is 1.77. The pH of this solution is, after taking 14 minus pOH, is 14 minus 1.77 equals 12.23.